Hello, everyone. My name is Sarah Chadwick, and thank you for joining EPA's Coalbed Methane Outreach Program for a webinar on abandoned mine methane as an energy source. Today's webinar will provide an overview of AMM as an emissions and energy source, discuss opportunities for AMM projects in the United States, and highlight an example of AMM project development. We will end today's webinar with a question and answer session. Please note that today's webinar will be recorded, and the recording and transcript will be posted to the CMOP website at www.epa.gov/CMOP within a few weeks. Before we start, I want to go over a few webinar software tips. So there are two ways to connect with the audio today. You can either listen through your computer speakers or use the number posted on this webinar slide. All participant lines will be muted for the duration of the webinar, regardless of the audio method you choose. Note that you may want to mute your computer speakers if you use the phone line to avoid any feedback. And if you are having trouble accessing the online portion of the webinar, you may have better luck switching your browser to Firefox or Chrome. However, if problems persist, you can find more detailed guidance at www.webex.com. And there are a few ways to participate in today's webinar. Throughout the duration of the webinar, you can enter questions into the Q&A box located on your screen. When submitting your questions, please select all panelists from the drop-down menu if you are able, and this will ensure that all of the speakers see your question. Questions will be moderated at the end of the webinar during the Q&A session. We also have a short comment form at the end of the webinar, which is a chance to provide feedback on today's webinar and future webinar topics. We really value your comments and will use them to inform future webinar planning. And the feedback form will pop up automatically at the end of the webinar or when you close out. So here's the agenda for today's webinar. First, we will hear from Valerie Ashkenazi, the head of EPA's CMOP program. Next, we will hear from Michael Cote from Ruby Canyon Engineers, followed by Evan Vessels from Vessels Carbon Solutions. As I mentioned before, we will end the webinar with a question and answer session. And I will now introduce our first speaker of the day, Valerie. Valerie is a program manager at the U.S. Environmental Protection Agency, supporting voluntary methane emission reduction programs in the oil and gas and coal sectors. She has an MPA in Environmental Science and Policy and over 5 years' experience managing pollution prevention programs at EPA. Take it away, Valerie.
Thank you, Sarah, and thank you everyone for calling into our webinar today. So before introducing our next speaker, I'd like to just quickly provide some background information about the CMOP program and share a quick update on some of our recent activities with you. CMOP, or the Coalbed Methane Outreach Program, is one of EPA's several voluntary programs focused on methane emissions reductions. We work with industry partners to support the capture and use of coal mine methane, or CMM, in the U.S., and focus on coal mine methane, or CMM, rather than coalbed methane, or CBM. Some of our past activities have included identifying profitable opportunities for CMM recovery and providing resources such as best practices to help overcome barriers to project development, including technical support, for example, to coal mines, sharing information with project developers, and working with other stakeholders. In the last 25 years, the CMM industry in the U.S. has advanced significantly so that over 80% of methane from U.S. coal mine degasification systems is now recovered and used, whereas it was closer to 25% in 1993 when the CMOP program began. Also, since the CMOP program began, we've reduced coal mine methane emissions by nearly 200 million metric tons of carbon dioxide equivalent, or MMTCO2e, through our outreach and technical assistance activities. In July 2019, we updated several of our resources, including information on CMM developments in the U.S., including an interactive map of current projects and potential opportunities for projects, and profiles of the 35 gassiest coal mines in the U.S. So some of these updated resources are listed here, but they're also available at our website, epa.gov/CMOP, and you might have seen a listserv message about these resources earlier this year. As I mentioned earlier, the CMOP program focuses on coal mine methane, or CMM, rather than CBM, but there are several types of CMM shown here, including ventilation air methane from active mines, surface mine methane from surface mines, drainage system methane from degasification systems, and also abandoned mine methane, which we're discussing today and which will be referred to throughout the presentation as AMM. The source of AMM is from abandoned mines. As mines mature and coal seams are mined out, mines might be closed or abandoned, but it's possible that even after active mining stops, the coal mine methane will continue to seep out through vent holes or natural fissures and cracks in the ground. So we'll be discussing AMM today, but please reach out to us if you have questions about any of these other sources of CMM. Next, I'd like to introduce our first speaker. Many of you might already know Michael Cote from Ruby Canyon Engineering. He's an experienced CMM and AMM professional. He's worked with our program on various aspects of AMM emissions, estimations, and project development since 2000, almost 20 years. He was one of the principal authors of EPA's AMM emissions estimation methodology in 2004, which is a methodology used by the Intergovernmental Panel on Climate Change, or IPCC, and EPA's current national greenhouse gas inventory. In 2005, Michael co-founded Ruby Canyon Engineering, whose services primarily target methane to energy offset projects at coal mines, landfills, and livestock operations. He's also a partner in Global Carbon Strategies, a company that developed and is currently operating an abandoned mine methane project at the West Ridge mine in Utah. He received his Bachelor of Science in Environmental Science and Management from Colorado Mesa University in 1997. Thank you, Mike.
Good morning or good afternoon, everybody. I will see if I can manage this first slide. Okay. Well, I think some of the key messages I'd like to convey today about abandoned mine methane, which we'll refer to as AMM throughout the talk, that it is a valuable energy source, and we'll see that most all of the projects that are in the U.S. are utilizing the methane in some form or another. Also, that there are current opportunities that do exist in the U.S. There are a number of abandoned mines, and it actually is a bit of a growing sector. As you know, that there'll never be fewer abandoned mines than there are right now. There'll always be more. Currently, there's close to 550 mines in the U.S. And so, I mean, I highlight here just a few of the more recently closed mines that we would consider as high candidates. These are probably some of the top, 30 or 40 gaseous mines in the U.S. And so I note here the Emerald Mine in Pennsylvania, Bowie 2 in Colorado, where there may be a project just under development, New Future Mine in Illinois, and also the West Ridge Mine, which actually has a project that's been operating for about 18 months. Also, there are some additional projects that if you go to the California Air Resources Board and their offsets program, you can see new projects listed, and there are several AMM projects currently listed that have not attained any credits yet, but are in the development phase. And one of the other things I think that message we want to convey is that pre-project assessments, understanding the resource, and also throughout the AMM production phase, constant evaluations of the gas resource and the producibility of the mine is paramount to the long-term economic viability of the project. Abandoned mine methane can exist in large quantities in some very large longwall mines throughout the U.S. It's a significant source of fugitive emissions. In most cases, they're diffuse emissions that are leaking to the atmosphere through cracks in fissures and shafts and other preferential paths. So it's not exactly a single point source. Abandoned mine methane is also very favorable characteristics, very comparable to CMM. We're talking about medium quality gas air, typically 40 to 80% methane, which is good enough for direct use in most engines. Also with the number of wells you need to drain a mine, it depends. Mines can often be drained with just anywhere from 1 to 4 wells. So it's not something that takes a large drilling operation. We find a lot of AMM projects that actually coexist with CMM projects. That is very common, most notably a number of the Consol mines in the Pocahontas Basin in Appalachia, as well as a number of the, formerly Jim Walter resource mines in the Black Warrior Basin as well. Some of the data that you will need to at least look at a mine and sort of see what you have. There's some basic information that must be obtained from the active mine phase, and you'll need a history of the active mine emissions and coal production to understand what the mine void is, how much coal has been mined out, so you can determine some kind of a gas in place number, the degree of which a mine is sealed, or the degree of which a mine may be flooding, or important information to have, and a lot of that is more anecdotal. And also, the date of abandonment is very important. There's a history of U.S. AMM emissions since 1994. You can see here that the resource has ranged somewhere between 18 and 23 BCF, looking at the top blue line. It's been about 18 BCF for the past 5 or 6 years. Similarly, the recovery operations in the red line below have been around 6 BCF of recovery. There actually is about 10,000 abandoned underground mines in the U.S., but as you know, many of the coal mines in the U.S. are not gassy. And so we're really just focused on a subset of that population, just the gassy mines. And so currently there's maybe close to 550 abandoned mines in the U.S. right now that are in the database and are included in the AMM inventory that the EPA conducts. And if we look at that, I divided it in sort of into thirds, and the top third of 6 BCF of recovery is currently going on from 45 mines, and it's actually 20 projects, so many of the projects have 2 or 3 mines associated with them. This one photo that you see here, the Corinth project in Illinois, has more than a dozen mines associated with it. EPA did a study a couple of years ago to try to high grade the remaining mines, and as we'll see later, there's probably about the top 100 mines would account for the next 6 BCF of gas, and then finally the bottom tier 6 BCF is probably spread across almost 400 mines or so. So the economic viability of that will be very site specific, depending on this proximity to an end user, or if it's co-located with active mines, then it can supplement. Taking another look at the utilization from those 45 mines that are currently methane is being recovered. Gas pipeline sales by far represents about 3/4 of the utilization. I think what we've seen is a lot of coal mine methane pipeline projects that have transitioned to AMM. As I mentioned earlier, in Appalachia, that has been the case. We have one big power project operating right now, but it actually accounts for 5 mines. And also, we've seen in the past several of the projects have sort of flip-flop between gas sales and electric power, depending on the year and the time. And finally, industrial end use, direct use. We have a couple of projects, and there may be more of these. Sometimes the very small-scale industrial use projects don't show up on the radar. And so you can see that while flaring is sometimes associated with these projects, all of these mines have end utilization. Here's a U.S. map, just sort of identifying the mines that we consider to be at least worth a look at, the ones that would estimated to be over 200 MCF a day. We consider that kind of a minimum level of economic viability. And you can see here there's several clusters. Appalachia is the primary spot. Northern Appalachia, there in southwest Pennsylvania, is a rather good spot. You can see a lot of identified sites there. Central Appalachia as well. The Pocahontas Basin are also a large number of mines concentrated there. Other areas further west, you can see the southern Illinois and right on the Indiana border. There is a collection of mines in the Heron and Springfield seams there that have proven to be very viable. And there's a few, and then you can see in the west, there's a few mines in Colorado and Utah. Here's a summary table that came from EPA document, Abandoned Mine Methane Opportunities, and from the database, trying to high grade what remaining mines are out there. This list is about 80 mines representing 5.5 BCF of potential recovery. There's a couple of things to remember about this is that, this is assuming that the mines are dry, assuming that it's 100% recovery. And so, again, this is a desktop look at trying to take 500 mines and move some to the top of the list. You can see West Virginia, Pennsylvania, Kentucky by far have the most mines and the most opportunity. This table is available in that report, and it's referenced at the bottom. I think that one of the biggest unknowns in this case will be the degree of flooding of some of the mines, and as you know, as many of you know, the mines that do flood out limits the AMM recovery potential drastically. Well, originally when we were tasked with coming up with an abandoned mine methane emissions estimation method, a decline curve or decay rate method was used. And again, this was, may not fit every mine, but we were trying to find one method that we could apply to, 400 mines. And so you can see it declines very rapidly. This is a hyperbolic form of the curve. And so while it drops very rapidly early on, it flattens out, and while it approaches zero, it never actually achieves zero. Here's an example of a mine that was pretty close to the EPA's decline curve. You can see here the production is in blue and the decline curve is in red, and underproduced for a number of years early on, but then is pretty much matching it later in its life. I think the important takeaway here is that it's shown that an abandoned mine methane project can last 15 years to some economic level. And so when you apply this sort of decline curve theory, what you find is that recovery early on is best. That's when most of the gas will be absorbed from the coal the quickest. And so if we took an example mine of 3.5 million cubic feet a day when it was active, and then it was abandoned, you can see that it produces a little over 4 BCF of gas over the first 5 years, but then it takes another 13 years to produce almost the same amount of gas. And I have a couple of more bar charts here. On bars on here, you can see the first 10 years is equal to the next 27 years. So I think that's important to get to these mines as quickly as possible to achieve most of the methane mitigation. And also, economically, it's the best thing to do as you're trying to get your returns early in the project life. There are some economic incentives out there for CMM and AMM development, and probably the biggest is the compliance offset credits under the California Air Resources Board program. Currently, the credits are going for about $14 a ton, and so that equates to over $4 an MCF of gas. And as many of you know, that gas prices nowadays, the actual value of the offset exceeds the value of the gas. The voluntary offsets that are currently in a couple of standards, one with the Verified Carbon Standard, or VERA, has been around for quite a while, and that follows a decline curve methodology as well. And the American Carbon Registry has just come out. I think I have expected December 31st, but I believe that that methodology is going to be published this month. And the American Carbon Registry has a little bit of a new approach on abandoned mine methane. In this case, they are not using a decline curve approach, but credit is issued to all methane that's recovered from the operations. And we see that there is some renewable, clean energy, alternative energy credits available for certain kind of projects in several states: Pennsylvania, Ohio, Indiana, Colorado, and Utah. And in Ohio and Indiana, those credits actually extend to pipeline gas, not just electricity sales. And while this is an incentive, it's not nearly the incentive that a compliance offset credit will give you. I think that, we did find a couple of projects that have participated in renewable energy credits. One in Ohio, I think at the Nelms mine years ago, they had a direct sales contract with Ohio State University and for their cogen unit, and that was quite lucrative for them. And on the other side of it, renewable energy credits in Colorado for an electricity project, while it did offer some revenue, didn't exactly move the needle when it came to the economic viability of the project. There are a number of technical, while there are economic barriers exist, of course, there are a number of technical barriers to AMM development. I mean, one, of course, is the uncertainty in the methane resource. How much gas is left in the mine, and can you extract 50% of it, 80% of it, all of it? And that's a big unknown going into it, and until projects get underway, you don't really know. Oftentimes, you do encounter difficult geologic conditions as well in the mine. Sometimes, permeability is a big issue during the active mine phase. When you're constantly shearing off fresh coal, you're able to get much more methane, and then once that operation stops, if you have low perm coal, its ability to desorb will be much. So it's not just about gas content, but also about permeability of the coal. Water flooding is another issue, as I mentioned earlier. That the amount of flooding could impede the amount of methane that could be recovered from a coal mine, and there's not a lot of documentation. This is not something that's monitored. I mean, the shoreline of underground coal mine water is something that may be forecasted, but it's difficult to know if it's not monitored. In most cases, if there is some kind of water discharge issues and water quality issues, then it will be monitored. But most of the time, it's not monitored. With today's sealing of coal mines and sealing off districts as the coal mines move forward, we find that compartmentalization could limit the amount of methane flow, where your wells may only access a certain portion of the mine because of the degree of sealing underground. The adequate piping and seals of a mine, something that if you're getting to a mine that's already been closed for a few years, you have no control of the quality of that, and that's something that needs to be assessed, because air intrusion into a mine as you are sucking methane out can be a real problem. And finally, remote locations can offer a challenge as well. Our West Ridge project is one where we're probably 5 miles from the nearest power line, so we have no access to electricity at the site and have to generate our own power. Well, evaluating the decline curve is one thing that sort of gets you started, but really evaluating the resource in the field is a much better way to go to understand how the mine behaves. And so getting some kind of a temporary flare and blower to go on some existing wells if they're there helps a lot in understanding the behavior of the mine. So flow testing, pressure testing, flowing the mine and shutting it in and watching pressure build up. There's a variety of ways that can help an engineer do a better gas resource analysis. Then once the project is going, that's the best, matching some kind of a decline to existing production is probably the safest thing to do. So in this case, you can see this project here. I think it was from an Illinois basin project, perhaps 2 years into the project. If you look out at the forecast, well, in 2012, 10 years later, they're expecting to have maybe 1.5 million cubic feet a day as a resource. But as the project progressed, you can see 5 years into the project, that endpoint moves up to 2.7 million. And then with even more data, the uncertainty is reduced after 8 years, forecasted at 2.5 million in 2012, and then once you did get to 2012 here, at 2.8 million was the final number. So again, I think this sort of retooling, recalibrating your model every few years is a very important step for forecasting your future gas resources. When you compare abandoned mine projects to CMM projects, you have to keep in mind that the size and scale is quite different. We're talking about much smaller projects that are 10 to 20% of the size of a CMM project. And so they're not going to be, it's something that take into consideration from the outset. There's nothing you can do technically to overcome this. Utilization technologies are pretty much the same because we're talking about medium quality gas. One of the probably advantages of abandoned mine projects is that you're not having to interface with the coal mine itself. And sometimes the activities of coal mines, in terms of the amount of gas that they're emitting from gob wells and other kinds of wells, are certainly all based on safety considerations and not delivering a certain amount of gas to your project for economic reasons. Gas ownership can change after a mine is abandoned. A coal mine may be able to operate a coal mine methane project with or without a gas lease, depending on the state and the location that you're at. Whereas if you're in an abandoned mine situation, the gas lease will be necessary. Also, permitting is similarly, a lot of times the coal mines will have all of their permits under one umbrella permit, and they're able to do things with blowers and satellite sites that when you go to apply for your permit for your one location, you'll find that the blowers and IC engines will have some NOx and CO situations that permitting is not a simple step, and this should not be overlooked as it could be quite costly. So I guess in summary, what we're showing is that AMM projects offer a little different set of opportunities and as well some different challenges than CMM projects. And one thing that we didn't talk about too much is preparing an active mine for methane extraction can be quite beneficial, depending on how compartmentalized the mine is or what a mine can do, thinking about helping out methane extraction once they leave can be very important. So if you're in early and you're cooperating with the mine right at that time, that's definitely a consideration to have. Also, performing some kind of resource evaluation at the beginning of the project and throughout the project, and updating that is really important to understanding the behavior of your mine. Well, thank you very much.
Thank you so much, Mike. So for anybody who might have joined us late, I just wanted to remind everyone that the slides from this presentation will be available online. And if you have any questions for Mike, please feel free to submit those now in the Q&A chat box in WebEx. And we're going to wait until the end of the presentations, but if you submit those now, we hope to have plenty of time for question and answers at the end. So now that we've covered some of the opportunities and challenges with recovery and use of AMM, we're happy to have a company sharing their on-the-ground experience with AMM project development and sharing their case study with us. Evan will be sharing lessons learned from the Elk Creek mine in Colorado. And Evan has had 8 years of experience in coal mine methane capture working for Vessels Carbon Solutions. He has experience in emission data collection, gas plant operations, and renewable energy credit or REC sales and marketing offset credits. Evan has also been involved in lobbying on behalf of methane destruction in Colorado and California.
Thanks, Valerie. My name is Evan Vessels, and I'm going to talk about predominantly our Colorado project, but I would like to mention we've also operated a Pennsylvania project, and we have operated on both active and abandoned coal mines. So this is a picture of our Elk Creek project, and it was mining quite a bit of coal when it was still operating, and we were able to get into that mine while it was still active, and we were producing for a short period of time while they were operating. They are currently closed. This is just a picture of the methane drainage system, and we are attempting to collect methane from more than one point in that drainage system, but currently we are only able to collect from one of the 2 points we'd like to, and I'll talk a little more about that later. This is a picture of our facility. It's actually quite small. We have 3 gen sets that can each generate 1 megawatt of electricity, and then we have a large thermal oxidizer. And the thermal oxidizer is currently running intermittently because we are at a point in the in production and along the decline curve where we're no longer running full time. The project scoping required an enormous amount of partnerships with different parties, and also required working with carbon registries so that we could produce carbon offsets. Currently, our thermal oxidizer has produced over 700,000 offsets, and the generators have produced over 300,000. The engines are pretty basic standard technologies, and they're able to run off a very low purity of methane. This is the compressor system where we get the methane out of the mine, and it is transported across a small ravine to our facility through a pipeline, and when it reaches our facility, we have some pretty nominal processes to clean the gas. We knock some of the heavy particulates out of the gas flow, and then we also knock some moisture out. However, gas that goes to the flare does not need any of this treatment. The flared gas and the gas for the generators have to be managed by a sophisticated SCADA system that stands for System Control and Data Acquisition. And this is how we make sure that we are also measuring our gas content and flow so we can secure carbon offsets. Unfortunately, we're not able to produce the full amount of methane as indicated by the decline curve that Michael mentioned earlier. And the problem is we are sucking too much air in from atmosphere. The reason why we know this is because we've detected oxygen in the gas streams, and oxygen bonds with coal to become CO2 in a very short period of time. So when we're detecting oxygen coming all the way to our facility, that means that it is there's a very large amount of oxygen coming in from the atmosphere, so much so that some of the oxygen is still reaching our facility, and this is preventing us from operating at full capacity. It is our opinion that we will have to seal a number of mine shafts if we want to extend the project to its full capacity, and there are at least 20 locations that are possible places for the gas to be either seeping out of the mine or oxygen seeping into the mine. And both of those are contributing to the fact that we cannot flare the gas. This is just a little shout out to our various partners who made this possible. This is a list of the various advocates we had, and it's particularly important to note the advocates because we would never have gotten all of the different parties together had there not been a champion within each of the various companies or associates that we had helping us build the project. And in particular, I want to mention Jim Cooper, who was the president of the mine and who was a strong proponent for us in communicating to corporate, their corporate management, the need or at least the benefits of capturing coal mine methane. So as Michael said, it's best to attempt to get into the mine when it's active. There's a lot of advantages to that. In order to do that, you have to promise not to interfere with any mining operations, and you need to demonstrate the benefits you can bring to their project, which includes destroying volatile organic compounds, which are regulated, even though methane itself is not. And we also provide a small revenue stream for the mine. It's very small, but it's there. And so the local support and partnerships were critical to getting this project off the ground. And in particular, Randy Udall was a very important advocate, and he was probably one of the most instrumental people in pulling the different parties together. The other important element, of course, was making the project profitable, and that was entirely due to California's cap and trade system. The cap and trade system is absolutely a fantastic way to monetize coal mine methane. Unfortunately, what didn't work in terms of getting the expansion of coal mine methane destruction was renewable energy. And in both Colorado and Pennsylvania, where we've operated, they have renewable energy programs that really did not lead to further electrical generation. And eventually in Pennsylvania, we shut down our electrical generation, and we only flare gas in Pennsylvania. It is important to note that electrical generation from coal mine methane is much more expensive than wind and solar. And so that's another weakness of renewable energy, since it values mostly the cost of electricity over the benefits to the environment, whereas cap and trade recognizes the benefits to the environment over anything else. We also ran into an enormous number of regulatory constraints. Currently, there's no framework in the states that we operate in to mitigate methane. So you have to permit through more traditional gas production sources, which are just not appropriate for coal mine methane destruction. We've also attempted to permit under mining, under the mining divisions in various regulatory frameworks, and that has not been helpful. We're currently trying to bridge the gap between mining and natural gas regulators and see if together we can figure out how to increase the capture and destruction of coal mine methane in Colorado. The BLM, who's a massive landowner in the state of Colorado in particular, but also in a number of states out west, are important parties here because they can either issue or not issue permits to work on their land. And while they have indicated they may be willing to permit methane destruction as simply methane destruction and not anything else, they have insisted on getting state regulators to agree to that first. I have included a little bit about the mine methane capture protocol because that is how we get our carbon offsets, which is, again, the main source of income for our company. Currently, California, Quebec, and British Columbia have a linked program for carbon offsets. And I just wanted to finish by mentioning that there is a significant lack of knowledge and understanding about coal mine methane in America, and there is a significant amount of opposition to coal mine methane capture and destruction. So it will require a significant amount of work to educate whoever needs to be involved, and it requires an enormous amount of repetition because you just have to keep returning and telling the same story over and over again until people start to get it. And that concludes my sort of lessons learned on coal mine methane and abandoned mine methane in particular.
Thank you, Evan, for sharing your experiences with us. It's really helpful to hear your best practices, and hopefully we can work together, everyone on the line and the CMOP program, to continue to address some of the barriers that you mentioned and challenges associated with AMM development. So we do have around 15 minutes for questions and answers. I'll pause here, and we will read questions off as they come in. There is one question already. I believe this is for Evan. How is the acid buildup on the gensets for Elk Creek Mine in Colorado?
We haven't had a significant problem with any kind of operations with the gensets. I'm not an engineer, so I can't speak specifically to the acid problem, but the gensets run about 95% of the time, and and by that I mean in a given year, each individual generator is operating for about 90% of the time that year, and you know, we take it down for general maintenance, and then we haven't had any problems.
Thank you. Okay, we have one more question from a professor at Penn State University. This is for Mike. Do you consider the differences between different mining methods, room and pillar and longwall mine? Longwall mining will have better AMM. Could you comment on that?
Sure. I think that when it comes to coal mine methane projects, mining method makes a big difference. Longwall mines typically, you know, generating a gob area create much bigger opportunities for methane recovery and use. When it comes to abandoned mine projects, I'm not sure that we've ever actually studied that. I would think that the same premise would apply, but there are some very successful abandoned mine projects in the Illinois basin that are all permanent pillar mines, and so that would be contrary to that. So I don't think we fully studied that on the AMM side of things.
Okay, there's a follow-up question to that, and then we have a couple of more. So to follow up on your comment, Mike, another question is about the decline curve. is the decline curve, is the experience-based or mechanism-based model, including the sorption capacity, diffusivity, and permeability. Let me know if you need further clarification there.
Okay, when originally the decline curve was developed, it was based on the characteristics of the coal gas content, sorption capacity, permeability. Then we were able to find not many venting coal mines that were abandoned to try to calibrate that model, and also it does follow along the lines of classic Coalbed methane decay curves. And so it's a bit of both, I'd say. And the one example I did show you in reality did match up quite well. But as Evan mentioned with their project, we find many fall well short of the decline curve itself.
Thank you. And before moving on to the next question, I want to let everybody know again that we plan to post the slides and a recording of this webinar on our website at epa.gov/CMOP, and also announce that through our listserv. So if you have not signed up for our listserv yet, you can do that by contacting myself, Valerie Askenazi, or check out the Contact Us page on the CMOP webpage, again, epa.gov/CMOP. For our next question, for Evan, you mentioned in your presentation that you plan to seal several vents. Could you please comment on why that had not been done earlier, or if you were not allowed to seal the mines, how that played out?
Well, currently we do not have any permits to seal the mine, and the reason why is because there are a handful of permitting options for an industrial activity, and sealing the mine is considered an industrial activity. It's considered a surface disturbance. And there's no regulatory framework to permit methane control over an abandoned coal mine. So we're attempting to go through some non-ideal permitting options. One is to permit through a coal mine, but the Department of Mine Reclamation that permits coal mine activity would require us to permit ourselves as a coal mine, which we are not. And there's an enormous amount of costs and burdens to that, and he assured us it could take years before we get permits to seal the mine portals, and by then the majority of the gas may have already leaked out. So another option we're considering is permitting through Colorado Oil and Gas, and we have also not been successful in securing a permit from them because they want us to produce gas from wells. They don't want us to drill into a mine shaft and seal up the mine shaft in a way that's much better than what's already been done to seal it. So they're not currently willing to permit mine sealing operations either. And then lastly, a number of these mine shafts are on BLM land, and they're not willing to permit a surface disturbance without a local regulatory agency that's willing to permit it for us. So we're kind of boxed in by a number of different regulatory agencies, none of which are willing to currently permit a surface disturbance for sealing up poorly sealed mine shafts and portals.
Thank you, Evan.
But we're still working with them.
Thank you, and that's actually a great segue into our next question, since you mentioned BLM regulations and how important that can be for project success. So this question is for both you and Mike. If there are any additional policy measures you might recommend to encourage AMM projects. You mentioned the different cap and trade programs, but this is an open-ended question. If there are any other effective policy measures you'd like to share with everyone on the webinar?
I think a low carbon fuel standard is one way you could go. We have not currently utilized a low carbon fuel standard, but we've heard good things.
I can echo what Evan just mentioned. Renewable natural gas is something that's really coming into vogue right now, and actually has value that could exceed carbon credits in the classic sense, like the California Air Resources Board. We're not so sure, since so many of the mines are unable to achieve the decline curve, they underproduce, that a methodology like the new American Carbon Registry methodology that allows you to get credit for all that you produce simplifies the process quite a bit.
Great, thank you. There was one more question for Mike. In your presentation, you mentioned one of the potential challenges associated with AMM project development might be flooding of abandoned mines. So I was wondering if this was a consideration at all at the West Ridge Mine project you've been involved in, or if you have any other general recommendations for ways to anticipate or deal with flooding at abandoned mines.
I guess my answer is no. I mean, water extraction. If you're pumping water out of the coal mine to produce methane, it is not eligible for carbon credits under the CARB program. And so also there's a whole water quality, water discharge permitting issue. So I don't think that in some ways the mine flooding is a methane mitigation activity, reducing. There is actually a completely separate decline curve for flooded mines where emissions typically go to zero after 15 years. So I think that there isn't going to be any interest in managing the water at the same time as the methane.
Okay, thank you. We'll have time for one or two more questions. Thank you everyone for, again, joining us. I'll pause here for one more question. I don't see any additional questions, so I think we'll wrap up our webinar here, but please again feel free to reach out to us with additional questions at epa.gov/CMOP, our contact us form, or the contact information for any of the presenters you heard from today. And thank you so much again to our presenters, Michael Cote and Evan Vessels, for sharing their experience with us. It was great to hear from both of you. For anybody still on the line, we'd appreciate it if you would consider providing feedback in the comment forum when you exit the webinar in WebEx. Thank you again so much for joining, and we look forward to the next webinar.